In this lecture, we will see what is harmonics or what are harmonics. And there are two different types of harmonic analysis. First one is called DC harmonic analysis. We will see its derivations, and we will also see AC harmonic analysis with its derivations. So upon the completion of this lecture section, you will be able to understand what is harmonics, basics of DC and basics of AC harmonics. And of course, we will also see some equations. You try to remember these equations. So power electronics, we had seen detailed overview of power electronics in the previous lectures. So what are the disadvantages and advantages of power electronics? When we talk about advantages, we can say so many points like here. So we have highly efficient design we can achieve by using these power electronic devices, because the loss is much lesser due to less loss. And these devices are highly reliable, and these devices are having long life and less maintenance. So if you once install the device in the circuit, you do not really need to worry about its damage or the lifetime, or whether it's going to break it because of extra reverse braking voltage and so on. Of course, in the data sheet, there are some limitations. If you exceed the limitations, then the device can get damaged. But if you follow the steps and procedures, then everything is going to be okay. And also it's less maintenance. And it has a fast dynamic response. The response is quite fast. The switching is quite fast. And requirement for heatsink and cooling system are less. When we talk about heatsink, in the typical way of implementing speed control, you will have kind of external resistor, and the resistor is going to dissipate the heat, dissipate the voltage in terms of heat. So if it's a really high voltage, then the heat is really quite high. The temperature will be very high. The circuit will be very hot, so it can easily get burned. That's why we wanted to use heat sinks and cooling fans. So cooling fan will always blow the air, cooling air on the circuit, so it will cool down the circuit. It will not get burned down. But when we use these P devices in the circuit or in the converter circuits, we do not have such a big problem. So we still need heatsink in some cases, but you don't need to have a very huge heat sinks and so on. I think you know what is heat sink. So we have a lot of heat sinks in our lab. You can see that. So for example, in this circuit, I don't know if you are able to see that. I also have the heat sink here. Okay, so we can see that in the physical lecture later on. Okay, heatsink is important for any circuit or any ICs to dissipate the heat easily. By using these P devices, we can achieve smaller in size, less weight, or compact size and less weight, low installation cost. So there are so many advantages due to these power electronics or power electronic devices. And we have one drawback. Even though we have so many advantages, we have one disadvantage, that is called harmonics. Due to switching, because we are using P devices as a switch, right? It's going to on and off, on and off. So due to switching and non-linear characteristics of load, harmonics are injected into the system. Okay, so these harmonics are injected into the system. When we get the output, we also get harmonics. Again, what is harmonics? What is the definition for harmonics? It is a non-fundamental component of current or voltage or power that is injected into the system, non-fundamental component. This is not a desirable. We do not want to have this, but this occurs automatically. Okay, so due to harmonics, what's happening? We know now harmonics are injected into the system because of the switching. So because of the harmonics, expected waveforms get deviated from its original form. So I am expecting some kind of, let me take my pen again. I am expecting some kind of sinusoidal waveform. Because of these harmonics, I am expecting these at the output. Because of the harmonics, what I am going to get, I am going to get kind of this original waveform together with some harmonics. So the harmonics are kind of non-sinusoidal. It can be in some cases, and they are periodical. So it will repeat periodically. Okay, so in harmonics, yes, because of the harmonics, we are getting distorted waveforms. Instead of having the smooth waveform, we get distorted, and we have higher order harmonics presence in the output. I will explain in a while what is higher order harmonics. So for example, if you give AC input, that is the sinusoidal signal, V of t is equal to Vm times sine omega t. So that is the mathematical representation of sinusoidal signal, Vm sine omega t. I am applying to a PE circuit. And if you plot its source current waveform, then it will be non-sinusoidal but periodic. So here you can see, so this is the output waveform. I'm expecting to have this kind of smooth sinusoidal at the output. But because of harmonics, I am getting distorted waveform at the output. Together with this output, we are also having so many harmonics. So second order harmonics, third order harmonics, fourth order harmonics, and so on. Okay, so we know how harmonics are happening. Due to switching, harmonics are injected into the system. Why harmonics are undesirable? Why we do not want harmonics? So any non-sinusoidal periodic source current waveform can be represented in terms of Fourier series. First of all, why harmonics are undesirable? I will explain here in a while. Before that, we have to go to some mathematical representation of the waveform. So as I said, any non-sinusoidal periodic waveform can be represented in terms of Fourier series. So remember, now we are going to represent the waveform in terms of Fourier series in order to analyze harmonic components and its presence. So that is how normally we work in industry, right? So when we have some problems, we try to make it in terms of mathematical formulas and equations, and then we try to then we do analyzing. We are analyzing how to remove those unwanted things mathematically, and then how can we implement this in practical. For example, in filter circuits, we are doing the same. So here also we have some kind of unwanted harmonics. Here you can see this is what I want, the fundamental component I want, but I have so many non-sinusoidal periodical harmonics and higher order harmonics. Okay, so how can we represent the waveform in Fourier series? So now I can write for current equation. So Is of t is equal to I0 or I suffix 0 or I suffix O, that is the DC component, plus Im1 sine omega t. This is the fundamental component. If this is going to be the AC voltage, then I am only after this one. And we have, this is called the fundamental component, Im1 sine omega t, plus Im2 sine 2 omega t. This is second harmonic, plus Im3 sine 3 omega t, plus Im4 sine 4 omega t, plus Im5 sine 5 omega t, and so on. So this is called a second harmonic, second order harmonic, third order harmonic, fourth order harmonic, and so on. Here we are getting this as an output, this complete equation. We want only Im1 sine omega t. We want only the fundamental component. We want only this fundamental component. We do not want all these things here. So all other components are undesirable. For example, I told about second harmonic, second order harmonic, third order harmonic, right? So second order harmonic means what? So second order harmonic component means it has angular frequency twice as of fundamental component frequency. And third harmonic component means it has angular frequency 3 times as fundamental component frequency. Fourth order harmonic means similarly it has angular frequency 4 times as fundamental component frequency. What is that mean? Maybe let us just take one example, then you will understand better. So now I have the sinusoidal wave. This is called the fundamental component. This is what I want. But second order harmonic means what? According to the definition here, second order harmonic component, it has angular frequency, which is twice as fundamental frequency. So here I have the period, right? This is the one time period. I have one frequency for this original fundamental component. So second order harmonic means I will have twice as the original. So here the same time period, instead of having one, here I have twice as the original one. So this is a high frequency. So this is a second order component or second order harmonic. Third order harmonic means what? Similarly here, instead of 2 cycle, and I'm going to have 3 cycles. So 1, 2, you can see here 3 times. So 3. Within the same cycle, the same frequency, we have 3 times. That is 3 times of the fundamental component frequency. Then fourth order means there will be 4 cycles, 4 sinusoidal waves, and fifth order means there will be 5, and so on. So these are harmonics. These harmonics are injected due to switching. But this is also coming at the output together with the original fundamental component, and the original component is also not as good as you can see here. They are distorted. So we had seen the previous slide, right? So we are getting distorted waveform. So the original waveform got disturbed. So now you have some idea what is second order harmonic, what is third order harmonic, what is fourth order harmonic. Angular frequency is just getting more and more. So now if you want to calculate total IRMS, so this is the current value. Now I want to find the root mean square RMS. Root mean square RMS value of this current IRMS. We need to add individual RMS values of all these components. So this current has several components. So this is the DC component, and this is the fundamental component, and this is second order component, third order component, fourth order component, and so on. Each component has certain RMS value. For here, this is the RMS value I0. Here, this is the RMS value Im1. Here, this is the RMS value Im2. So RMS means you have to go 1 by square 2, right? 1 by square root of 2. So now that is what I'm going to do. So I naught square plus 1 by 2, because here I am putting this 1 by 2 in the top, so to represent the square. So im1 square plus im2 square plus im3 square plus im4 square, and so on. This is the total current and its RMS value. So we are just taking out the component, the constant of each component, and then we are making it square. So instead, this is the only current we want at the output. This component belongs to, sorry, this constant belongs to this component, right? Fundamental component. This red color, this is what we want. But at the output, we are also having this I0 and IM2, IM3, IM4. So we are adding everything together and we are getting at the output like this. This is the output. So because of these harmonics, the value of IRMS, the total current value, total output current value is high. So IRMS is increasing due to harmonics. Okay, this is, you can understand naturally. And copper loss, because of the high current, of course, it's flowing through the copper, the conductor, then there is also copper loss increases. This is another drawback of harmonics. And we know the power formula, P is equal to VI cos pi. Cos pi is a power factor. Do you remember? Have you studied about these things earlier? Okay, so power factor. Because of this increased RMS value, power factor will get reduced. But if the power factor got reduced, then the efficiency of the entire application, either it's a machine or generator, AC machine or DC machine, the efficiency will go down. So we do not want the power factor to decrease. So what can we do? So right now, we know we are getting these harmonics, and because of these harmonics, there are so many side effects. It's affecting the entire system, its efficiency, it increases the copper loss. So we want to avoid these harmonics. So harmonics are really making issues in some applications like rotating machines, transformers, relays, and so on.